In this video, I'll show you some examples of using rules to compute antiderivatives. Here are the functions we are going to consider in this video. Pause the video and attempt to find antiderivatives for each function. You can check each of your answers by calculating the derivatives of each of your answers and seeing if each derivative is equal to the corresponding given function. Did you find them all? Let's go through these together. We'll start with f of x and use a capital F to denote the antiderivative. Let's first focus on the square root. We don't have any rule that explicitly says how to find the antiderivative for a square root, but we can rewrite it as x to the 1/2. In particular, we can now use the rule for x to a power. In this case, the p is 1/2. Using this rule, we'd have 1 over 1/2 plus 1 times x to the 1/2 plus 1. So this will be the first term in the antiderivative, and we can rewrite the 1/2 plus 1 as 3/2. We'll save that plus c for the end. Next, for the quotient. There is an x in the denominator, and we have a rule for finding the antiderivative for 1 over x. To use the rule, we can factor out the 7/8 in the term. So the antiderivative will include the natural log of the absolute value of x, and since the term was multiplied by 7/8, we'll do this for the antiderivative too. Now we add the plus c to get a general antiderivative for f of x. Next, let's look at g of x. Since this is a sine function, let's look at the corresponding antiderivative rule. The general antiderivative for sine of x is negative cosine of x plus a constant. But we have sine of 2x. So we might guess capital G of x equals negative cosine of 2x plus c. And then the antiderivative would be negative cosine of 2x. Since the original little g of x didn't perfectly match the rule, we should check to make sure the derivative of capital G is equal to little g. In the derivative, we'll need to use the chain rule, so we get sine of 2x times 2. And if we compare these, we see that they're not equal. So this guess wasn't correct. But we weren't too far off. We were off by a multiple of 2, so maybe we just need to divide our guess by 2. Let's try doing that. So our second guess is that the antiderivative of little g is negative 1/2 cosine of 2x plus c. Let's check to see if this works. Using the chain rule, we'd get negative 1/2 times negative sine of 2x times 2. Multiplying these two negatives gives us a positive, and these 2's cancel each other out. So this is all equal to sine of 2x, which matches our original little g of x. This means that our second guess was correct, and we have found an antiderivative of sine of 2x. Next, let's look at h of x, which is secant of 5x times tangent of 5x. We have a rule for secant tangent. The antiderivative is secant. Now we have a 5x instead of just an x. So we could try using that in our antiderivative. Before, when we had a 2x inside the sine function, we ended up having to multiply by 1/2. So let's try multiplying by 1/5. So our guess for the antiderivative of h will be 1/5 secant of 5x plus c. Let's check our guess by computing the derivative of capital H. Using the chain rule, we'll get a derivative of 1/5 secant 5x times tangent of 5x times 5. And the 1/5 and 5 cancel each other out, giving us a derivative of secant 5x times tangent of 5x. And this derivative is the same as our original little h of x, telling us that capital H is the correct antiderivative. Next, let's look at k of x. If we look at the first term of k, there is a variable in the exponent. This means that it's an exponential function, and we can use the corresponding rule to compute its antiderivative. In this case, the base is equal to 2, so we'll use 2 in the antiderivative formula. So, for the antiderivative of little k, the first term should be 1 over the natural log of 2 times 2 to the x. And since the first term in little k of x is a coefficient of 5, we'll multiply the first term in the antiderivative by 5. Next, let's look at the second term of little k of x. In contrast to the first term, the second term has the variable in the base raised to a fixed power. So, we'll use the rule for antiderivatives of powers with an exponent of 2. This gives us 1 over 2 plus 1 times x to the 2 plus 1, which we'll use as the second term in the antiderivative. Little k of x has a coefficient of 5 in its second term, so we'll multiply the term in the antiderivative by 5, and then add the constant c. Now we have a guess for the antiderivative. We can check this by computing the derivative of capital K. The natural log of 2's in the first term cancel, and the 3's in the second term cancel, which gives us 5 times 2 to the x plus 5x squared. This is equal to little k of x, so capital K is an antiderivative of little k. For our last example, let's look at e to the x. The derivative of e to the x is e to the x, so the antiderivative should be e to the x plus c. But we have a rule for exponential functions. Would it work here? If we use e as the base, then the rule looks like this, and our antiderivative would be 1 divided by the natural log of e times e to the x plus c. But the natural log of e is equal to 1, so this antiderivative would simply be 1 times e to the x plus c, which matches our guess. So the antiderivative formula also works for e to the x. To summarize what we've done, we started with these 5 functions, and we used the rules to compute antiderivatives for each of them.